welcome to this month's Night Sky News with me, astrophysicist Dr. Becky Smethurst. This is the series where we take a look at what to look out for in the night sky in the next coming weeks, and we chat about what's been happening in space news in the past month, including this month for October, the first planet detected in another galaxy outside the Milky Way, and a supermassive black hole that spaghettified a star. So excited to chat about that one, seriously. Anyway, any research paper I mentioned in the video will be linked in the video description below, and I've got timestamps if you want to skip ahead to any specific story. So without any further ado, let's kick this off and start by looking up. So the next few weeks are all about meteor showers. We've just had the peak of the Orionids meteor shower, so those are still hanging around in the sky at the minute. Then in early November, you've got the peak of the Taurids, and then in mid-November, you've got the peak of the Leonids as well. So a meteor shower happens when the Earth passes through a region of space along its orbit that has a few bits of rocky rubble, usually left over by like a comet on its journey around the sun. And depending on where that rubble is left, the meteors appear to come from a specific place in the sky, like a constellation. For example, the Orionids appear to be coming from the constellation Orion, hence their name. So what you want to do with a meteor shower is look anywhere but the constellation they're supposed to be coming from, because they're going to be streaking away from that point. So if you're looking at the constellation, you're not going to see them as they streak up and over your head. So the key to meteor showers is, first of all, patience, because, you know, there's meteors every couple of minutes or so, one or so a minute. You know, it's not sort of looking like meteors falling like rain. That only happens maybe once a decade or so if we're lucky. And the other thing is to lie flat as well, because then you'll see more of the sky than if you're looking sort of craning your neck as well. It's much more comfortable to just lie flat. So wrap up warm, put a blanket down, stare at the sky until you see something streak across it and it takes your breath away. So the Taurids meteor shower in early November, that's going to appear as if the meteors are all coming from the constellation of Taurus, which is just above Orion. So if you can find Orion, turn away from there. In the northern hemisphere, they're going to peak around about the 11th and 12th of November. And in the southern hemisphere, the peak will be about on the 5th of November. You want to look around midnight local time, wherever you are, northern or southern hemisphere, for the peak, which will be around about 5 meteors an hour, which isn't great, to be honest, on the sort of meteor shower scale. It's only maybe about 1 every 12 minutes or so. But the Taurids is known for its exceptionally great bright fireballs. So much bigger meteors, instead of being caused by something like a speck of dust burning up through the atmosphere, maybe you get something that's like pebble-sized that burns up in the atmosphere that's so much brighter and more spectacular. So if you see something like that in the next few weeks, that's probably what it is, a sort of Taurids fireball meteor. So keep your eyes peeled. Then we've got the much more impressive Leonids meteor shower peaking on the 17th of November. This is visible for both northern and southern hemispheres again. And the peak of this meteor shower, there'll be about 10 to 15 meteors an hour, which is more like 1 every 4 to 6 minutes. So much more chance of spotting them. However, instead of looking around midnight, you have to look for these sort of before dawn, which I know is not everyone's favorite time to get up. But if you are up early, then get up and you want to face away from Leo, hence Leonids, the name, towards the east. So face away from wherever the sky is brightening because of the rising sun, and look for meteors anywhere but there. All right, so as well as meteor showers, we've also got all 5 major planets visible in the night sky at the moment, wherever you are across the globe. First up, we've got Venus and Mercury in the east right before dawn. So look towards where the sky is lightening. Venus is the brightest thing in the night sky after the moon, so it's a little bit difficult to miss. It should be the last thing left in the sky before the sunrise. It should be the only thing that you should be able to see as the sun brightens and brightens the sky as we get closer to sunrise. Mercury, however, is much fainter. It's also much closer to the sun, so it doesn't rise as high in the sky, making it a little bit more difficult to spot. The closer you are to the equator, the higher it will be for you, and it will be much easier to spot, hopefully. And also the closer you are to the 10th of November, because that's when it will actually reach its highest point in the sky as well. So keep an eye out for that if you can. Then we have Mars visible all night, rising in the east and setting very early morning in the west. Looks very bright at the moment since Earth and Mars are so close together in their orbits. You know, back in mid-October, they sort of passed that closest point of approach, because Earth and Mars' orbits aren't circular, they're sort of oval shaped, so there is a place where they come a little bit closer together. Mars gets incredibly bright in our sky, brighter even than Jupiter, so it's very easy to spot, especially with its very distinctive sort of rusty red colour as well. Speaking of Jupiter, that's also visible in the night sky at the moment in a beautiful little pair with Saturn in the south in the evening. They usually set sort of around midnight, maybe before that, depending on where you are in the world. They're very distinctive at the minute because they're in that pair. They're some of the first things to appear in the night sky after the sun has set as well, because they're so much brighter than all the fainter stars. And because Jupiter is one of the brightest things, it's difficult to mistake for anything else, especially just after sunset. And it makes spotting Saturn really easy too, because once you found Jupiter, it's like, oh, and there's Saturn next to it with its very distinctive sort of like yellowish tinge. If you're in a city, it's probably even going to be easier to pick out Jupiter and Saturn because the light pollution will wash out all of the fainter stars in the background, leaving probably just the planets looking very, very bright and beautiful in your sky. However, if you're still not sure that what you're looking at is what you think it is, then I've got a couple of tips for you. So tonight, this evening, the 22nd of October, a half moon is going to be right in the middle of Jupiter and Saturn. And then by tomorrow on Friday, it will have moved just past Saturn. But either way, if you can find the moon tonight or tomorrow, then you should be able to pick out Jupiter and Saturn in their pair very close to it. Similarly, on the 29th to 30th of October, you're going to have an almost full moon very close to Mars in the sky. So if you can find the full moon, you know that the reddish bright thing next to it is Mars. They'll be moving across the sky together all night, so it doesn't matter what time you look for this. Perhaps you might be doing some early trick-or-treating, and it'll be a fun sort of spooky thing to look for in the sky. Then on the 12th to the 13th of November, I couldn't skip out the fact that we're going to have a toenail moon, or a crescent moon, because I'm weird and I call it a toenail moon, right next to Venus and Mercury in the very early morning sky, just before dawn. It really is one of my favourite pairings to look for in the sky because the moon is so beautiful when it's a toenail and Venus is so wonderfully bright as well. They just look so good together. So if you manage to capture a picture of that pairing or a picture of any of the pairings I've talked about or any meteor showers as well, please do send them my way on social media because I love, love, love to see them. But now we need to talk about the space news that's been happening in the past month. All right, so as usual, there are far too many things for us to talk about for one video. So here we're going to be keeping the focus on black holes and high energy stuff, whereas over on my Instagram stories and on my YouTube stories now too, for all of you who don't have Instagram, we're going to be keeping more of an astrobiology focus. I'm going to be chatting about the potential discovery of lakes on Mars, but then also the discovery of glycine on Venus. Glycine is one of the most basic amino acids, which are the building blocks for life. So that was a really intriguing discovery, especially off the back of the announcement of the detection of phosphine on Venus from last month, which I talked about in last month's Night Sky News, if you haven't checked that out yet. So if you're interested in hearing about that, head over to my Instagram or my YouTube stories. They should be going up live after this video goes up. But here, for now, first of all, I want to talk about the potential discovery of a planet, not in a star in our own galaxy, the Milky Way, but orbiting a star in another galaxy. So in the past 25 years, we've seen our knowledge of other planets not in our solar system but orbiting other stars in the Milky Way go from 1 in 1995 to over 5,000 in 2020. But all of those have been found orbiting stars in our own Milky Way. And they were found either by taking a direct image of that star and blocking out the light from the star so that you could just get the light from the planet, or watching a load of stars and waiting to see if any of their brightness is dipped because a planet passed in front of them from our perspective. But what about if we wanted to detect an extragalactic planet? So a planet in orbit around a star in another galaxy entirely. It's very likely that they exist since, we found so many planets around stars sort of in the general vicinity around the sun. It's just proving that they're there is so difficult because we can't use the same methods that we do to find planets in the Milky Way because looking for changes in brightness as a planet dips in front of its star at that distance, they're just too faint to see. But what if we could use something like X-rays instead. X-rays are incredibly energetic. The objects that produce them are so bright. We can see them at much further distances, and they're much rarer as well. So you can much more easily pick them out from the background of 100 billion stars in this other galaxy. Much easier to pick out an X-ray source than it is to pick out a single star. That's exactly what Di Stefano and collaborators did this month with an X-ray source in the Whirlpool galaxy, Messier 51. It's a very famous spiral galaxy. It's about 23 million light years away. And this X-ray source is 1 million times brighter than the sun. It's what we call an X-ray binary. It's either a neutron star or a black hole, one of the two, in orbit around another normal star. And essentially what the neutron star or the black hole is doing is stealing matter from the normal star to add to their own mass. And that essentially happens, they drag the mass off the normal star and it ends up spiraling around the neutron star or the black hole. And essentially what happens to that hydrogen gas, that matter, is that it starts to heat up. It actually gets superheated due to how fast it's actually orbiting around the neutron star or the black hole, and it starts to glow in X-rays. Now, the region that those X-rays come from is actually incredibly small. Think about it, a neutron star the same mass as the sun is actually only about the size of a small city. So the glowing material that's orbiting around it is also only going to be quite small, smaller than your average planet, which means that if a planet is in orbit around this binary star system that used to be probably just two normal stars and one of those went supernova to give you a neutron star or a black hole, if you've got a planet in orbit around that and it happens to pass from our perspective and our line of sight in front of that X-ray source, then it's big enough to completely block out all the X-rays, which doesn't happen when we look in optical light, for example. If you have, like in our own galaxy, the Milky Way, when we look for planets, if you have a planet pass in front of a star, it's not big enough to block out all of the star's light, so we only see a dip in brightness of sort of a fraction of a percent. Whereas if we were looking at this X-ray source in another galaxy and a planet bigger than it passed in front of it, we would see the X-ray brightness drop from 100% to nothing as the planet passed in front of it, making it much easier to spot. So Di Stefano and collaborators observed this X-ray source M51ULS1 for 47 hours straight, and in that time, luckily, saw the X-ray light from it completely drop to zero for about 20 to 30 minutes. You can see that here in this plot of the count of the number of X-ray photons they've detected on that y-axis against time on the x-axis. You can also clearly see it in this X-ray image of M51 before and then also during when that X-ray source completely disappears. So essentially that X-ray light has been eclipsed by something, some object or other. And the question is, what is that object? Is it a planet, or is it something like a white dwarf star, which is what will happen, sort of be left over when the sun runs out of fuel? Is it something like a brown dwarf, which is kind of like a failed star, or a red dwarf, which is sort of a star that never really got off the ground very well? It's not very bright. So what you can do is look at the duration of the eclipse again and look at how long the eclipse lasted. And from some assumptions on the size of the X-ray source, you can then get at the size of the object that did the eclipsing. And they found that the most likely size for this object is something around about the size of Saturn. So that probably rules out things like brown dwarfs or red dwarfs, because they tend to be much bigger than even Jupiter, never mind Saturn. And the authors also pointed out that, okay, a white dwarf might be around about that size, but a white dwarf would also have acted as a gravitational lens and actually brightened the X-rays behind it because the white dwarf is so dense. So the authors concluded that the most likely object that this thing was a planet in orbit around this binary star system. At least a candidate planet is what we call it, because it's not confirmed for definite that it is a planet. That's just like the most likely hypothesis, most likely working hypothesis at the minute. But still, the first candidate extragalactic planet, still pretty cool in my book. All right, moving on, but sticking with the black hole theme, let's chat about the latest news from the Event Horizon collaboration, famous for their first ever image of a black hole. This one of the supermassive black hole in Meteor 87. You can see what I was talking about before, the light from the material that's been superheated as it spirals around the black hole. Now, whilst we're all sat here patiently waiting for the same image, but from our own supermassive black hole in the center of the Milky Way, which apparently is proving to be a little bit difficult because you have to sort of look through all of the stars and the gas and the dust towards the center of the Milky Way, and they're sort of, very contaminant foregrounds that you have to remove to make sure that you're only really detecting the light from around the supermassive black hole. In the meantime, whilst they're puzzling on that one, they have released a study on the change in the light from the material spiraling around M87, and they have found that it is wobbling. So that eventual image they released last year was from data taken in 2017 over a week with 10 telescopes across the entire world combined to give one Earth-sized telescope. And that's essentially because the bigger your telescope, the less blurry your image. Before that, though, there was obviously a lot of testing and commissioning and calibration that was done to prove that this actually would work. So through 2009 to 2017, they actually took a lot of these images, but say with only 3 or 4 telescopes joined to give you a continent-sized telescope rather than an Earth-sized telescope. And so they were seeing the same thing, but it was obviously a lot more blurry. They couldn't actually get the detail they needed to reveal that structure of what we call the accretion disk, that disk of material that's spiraling around the black hole. But once they had the final image and they knew what that eventual detail would look like, they could use that to infer what they would have seen with 10 telescopes if they'd had them back in 2009 when they'd only had 3 or 4 telescopes to combine together. They could sort of up the detail in the image. It was sort of like the actual equivalent of shouting enhance in a movie. What they found was that back in 2009, it looks mostly the same, except the brightest spot on that sort of donut of the accretion disk moves around from 2009 to 2017. That bright point is where the material is hottest. It's also probably the material that's going to be accreted by the black hole first as well. So it's very, very interesting that that bright spot moves around on such relatively short timescales, astronomically speaking. It's less than a decade, only a couple of years, and we see variation. So it all feeds into this question of how do black holes grow? Is it a very constant process where gas from that accretion disk that's orbiting the black hole falls in at this constant rate? Or is it more of a sporadic process where clumps of matter will occasionally randomly clump off that disk and fall onto the black hole? These observations suggest that over the past sort of 10 years that they'd observed the black hole at the center of M87 and seen that clump of material moving around and the disk wobbling around, that it could actually be that sporadic process where clumps fall off the accretion disk and onto the black hole. But then that raises questions of, well, how does that affect the black hole itself? I think black holes are very poorly named because it means that people end up picturing them as a hole that stuff falls into, but actually they're this huge mountain of matter, right? That's just this huge collection of mass in this very small, dense space. And so does the way that they grow with these clumps falling into it, or whether it might be a constant rate, does that actually affect the black hole itself? So, like most studies in science, I think this answers a few questions, but it ends up raising a hell of a lot more. All right, sticking with growing supermassive black holes, but this time one that is only 215 million light years away from Earth, practically a stone's throw. So most black hole growth is from this disk of material orbiting the black hole that we were just talking about. But it's also possible that a star or a clump of gas might just get a little bit too close and get spaghettified by the black hole. That is a real scientific word, and it also just happens to be my favorite word in the entirety of the English language. It's actually a really good description of what happens in the strong gravity around a black hole. So say if you were falling feet first towards a black hole and the gravity was pulling you down, the gravity would be so much stronger at your feet that would be slightly closer to the black hole, that they would feel a stronger pull than your head would slightly further away from the black hole. And eventually what would happen out is that you'd get stretched out into spaghetti, probably until you were just this spaghetti line of atoms just all the way down to the black hole. This can also happen to a star, and when it does happen, a huge burst of light is released on its way down to the black hole. And this month, Nickel and collaborators caught this happening to a star around a supermassive black hole in a very nearby galaxy. It was the closest that's ever been detected. Now, astronomers call these tidal disruption events, or TDEs, and they're pretty rare, actually. What you actually observe is just that brightening of the star as it gets torn apart by the black hole, but it's observed across all wavelengths of the electromagnetic spectrum because it's such an energetic process. You don't obviously see the gas of the star getting ripped apart like I've been showing in these nice simulations of what could be happening around the black hole. So the one Nickel and collaborators have spotted was called AT2019QIZ, and it was first spotted by the Zwicky Transient Facility, a telescope which essentially looks for any changes in the sky night after night after night. So it spots everything from asteroids to supernova to these tidal disruption events. So because the Zwicky Transient Facility managed to spot it so quickly after it had actually happened, it meant that Nickel and collaborators managed to follow up very quickly with lots of other telescopes, everything from looking at it in the optical to the UV to the X-ray. And so using all these, they could then figure out what had actually happened in this TDE, and they found that the supermassive black hole was probably a little bit on the small side for supermassive black holes, probably only about 1 million times the mass of the sun. Compare that to M87's black hole, which is like 4 billion times the mass of the sun. You're 1,000 times smaller here. And the star that got ripped apart by this black hole was probably around about the same size as the sun. So a fairly average system, astronomically speaking, but what was really special about this tidal disruption event was that the astronomers detected an outflow from the region around the black hole. So not the black hole itself, because nothing can escape a black hole, but literally an outgassing or throwing out of material from this region around the black hole as this star got torn apart and pulled in to the black hole. The way they spotted this was that they actually spotted the fact that some of the emission of light from this material that was going very hot had been blue shifted, i.e. it was coming towards us. It was being thrown out from the regions around the black hole at a speed of 10,000 kilometers a second. That's pretty fast. So what these researchers actually found was that the majority of light that they detected was actually coming from that material that was being outflowed at those huge speeds, rather than the material that had reached those huge speeds spiraling around the black hole and was about to be eaten by it. Which means that actually when that star came in, the majority of its material ended up being thrown back out again rather than being eaten by the black hole. That might sound strange to some because we think of black holes as just these endless hoovers that can just take in as much material as they want. But actually, you've got this material sort of jostling to all being eaten by the black hole. So the pressure builds and builds and builds and builds. It can't all be eaten at once, just like when you pull out the plug from your sink, not all the water goes down at once. And sometimes when that pressure builds to a certain amount, to ease that pressure, what happens is that material is thrown back out from the accretion disk in one of these outflows. We sometimes call them winds as well. And if you've got a very energetic system, then sometimes you also end up getting these huge big jets that can be funneled by magnetic fields and all sorts. So again, this feeds back into how do black holes grow? When a star or a clump of gas gets spaghettified like this, actually the majority of it won't get used by the black hole to grow. The majority of it will get thrown back out into space. And so the question is, can black holes grow more efficiently with lots of these spaghettification processes? Or would they grow more efficiently if they had a constant supply of gas that was feeding one of these accretion disks around them? And what it looks like from this result anyway is that in these spaghettification scenarios, try saying that twice as fast, spaghettification scenario, spaghettification scenario, spaghettification scenario, is that actually not as much mass as we thought ends up getting accreted or eaten by the black hole. That's it for this month's Night Sky News. Don't forget to head over to my Instagram or my YouTube stories to check out all of that astrobiology news in the solar system. But also, I just want to acknowledge that it has been 2 years since my very first Night Sky News video back in October 2018, and really 2 years since I started this channel as well. I remember that video got something like 200 views in its first day, and I was like amazed. I was like, 200 in a day, this is incredible. And you know, look at us now.
Look at us. Look at us. Huh? Who would have thought? Not me.
With books and plaques and thousands of you now watching, I still kind of can't quite wrap my head around it as I sit here alone in my spare bedroom talking to nobody is what it feels like. But I guess what I can believe is just that there are other people out there that just love this stuff as much as I do, and that is really what makes me smile. And I just want to say a massive, massive thank you to all of you from the bottom of my heart for being here, for commenting, for just engaging in chat about space, because at the end of the day, that's what I love to do. So thank you. Oh, so fluffy today. To any specific stories. So without further ado, on Venus last month, which was in my previous Night Sky New episode. So, Night Sky New episode? A short time scale, astronomically speaking anyway, of only a couple of decades. Years. 1 decade. Less than a decade. Couple of years. You're accreted by the black hole too, like the first clump of material. Bleh. And I detected those X-rays from your intergalactical planet. I love it. I should pitch McFly now, shouldn't I, for a parody song?